Okay, so we've covered measures of central tendency, and now we're going to look at measures of dispersion. So consider that we have, company A and company B. And we have some sort of aggregate review score out of 100. Both companies have maybe an average review score of 70. So both kind of have, an X bar around 70. But company A, sorry, that was a little bit too high. Company A is like, if we look at the distribution of scores, it's like consistently mediocre. This is 100. You never really get 100, and you never get really bad service. Company B often gets really bad service, but sometimes you get really good service as well. I'm deliberately not drawing a normal distribution. This can be any sort of distribution. So there's kind of greater variation in the second company. And the idea here is that, you have a mean. So you have like an X bar for the sample and mu for the population. But that's not really significant to kind of characterize the population very well, because the variation can be like very, very important. So kind of measures of, sorry, measures of dispersion. The first is the range. The range is literally going to be, let me just have a little snip here, is going to be the maximum minus the minimum value. So say, for example, we have our Facebook data, I think, number of Facebook friends from before. We literally take the max range is the max value of xi minus the min value of xi. Let me just draw the brackets properly. And so, for example, here we have a high score and a low score, and it's the difference between the two. And the interquartile range, let's just go back here. This is just the 75th percentile minus the 25th percentile. So here, if you think of the interquartile range, when we do our box plots of our data, and these are all of our data points. We've got a few more out here. We have the 75th percentile. And the 25th percentile. And so we'll call that Q3, Q1, and the IQR, I think we talked about this when we did percentiles, is Q3 minus Q1. Now, the most important thing is we're going to get onto some kind of measures of overall deviance, and overall deviation. So for a think, this is just how far we are away from the mean. So it's some kind of standardized measure of how far we are away from the mean. So here we have the deviance, and we have the total deviance, and we could actually have the average deviance divided by n. So let's go back to our whiteboard. Let's move that little example up a little bit. So we finished off with our, let's just say we finished off with our previous simple data set, and we've just developed a new one. So we have data set 1. And again, it's these reviews. We're going this time like from 1 to 8 of maybe 2 restaurants. And we have reviews of 4, 4, 4, 5, 5, 5. Data set 2, we have 1, 2, 4, 5, 7, 8. So both of these, if you add them up, we have sigma x equals 5 threes of 15 plus 12 is 27. And x bar is going to be the sigma x over n, so it's going to be 27 over 6 is 4.5. And the second one, unsurprisingly, 8, 7, 15, 20, 24, 26, 27. Something might tell you that I deliberately picked those with the same means. And again, we have 4.5. So this is the idea of 2 distribution. It's basically my restaurant with consistently mediocre, but on a scale of 1 to 8, and a restaurant that you either have like really good or really bad service. Okay, so let's just have, calculate the sum of the deviations. So the sum, so let's just say the sum which is sigma I equals 1 to n xi minus x bar. So this is just the difference from each of these guys to the mean. And so let's look for data set 1. We've got xi4 minus 4.5 minus 0.5 plus minus 0.5 plus minus 0.5 plus 0.5, 0.5. Oh, it all cancels out. And for the second one, it's going to be very, very similar. So 4.5 minus 3.5 plus minus 2.5 plus minus 0.5 plus 0.5 plus 2.5 plus 3.5. It's the positive and the negative. They basically just cancel out. It's kind of almost from the definition of the mean. So that's not really helping. That's not really helping us very much. But what we can do, if we want some measure of, the average or the total of how different things are from the mean, we could do 2 things. And in class, I would ask you what you could do. Well, you could do more than 2 things, but here are 2 things you could do. We could do xi minus x bar squared. and we're going to call this the sum of squared error. Or we could maybe do the sum of the absolute error, and we just do sigma I equals 1 to n, and xi minus x bar, and then we draw the line to the right, the absolute, which is basically take the positive value of each of those differences. Now, the thing is, we're going to actually do the first of these because this statistics is based a lot upon the squared errors and the variance that comes from the squared errors. But in terms of actually finding this measure of dispersion, the absolute value would also be a useful measure as well. And in fact, when I do, my data mining class, we actually have measures of absolute error as well as the sum of, the squared error. So let's just go to my data set here. We'll remove that for the moment. And let's just calculate the sum of squared error. Okay, so the sum of squared error here for data set 1 is going to be minus 0.5 squared plus minus 0.5 squared plus minus 0.5 squared, and then 0.5 squared 3 times, because each of these values is 4 minus 4.5, 4 minus 4.5, 5 minus 4.5, etc. And so what do we get here? We get, I still kind of want data set 1 up. Actually, I've been writing, tell you what I'll do. I'll just make my writing a little bit smaller. That's better. So we're going to get 6 times 0.25 is 1.5. And the sum of squared error for data set 2 is minus 3.5 squared and that is actually, I need the calculator to do that one. That is actually 37.5. So this is all well and good, but we want some kind of standardized measure that doesn't depend on the size of the data set. If we don't want it to we add another 20 restaurants and then this value is going to get bigger and bigger and bigger. And we want some kind of standard measure that's, not relative to the size of the data set. So what we're going to do, we're going to first do the population. We're going to define sigma squared equals 1 over n. This assumes we have the entire population. just keep that for the moment. And for a sample, okay, so it's pretty much exactly the same. Now, there is a mathematical explanation. I will actually post this online. It's a little bit beyond what we're doing in this class in terms of a mathematical class, but let me just show the pens. This is to basically accounting for the degrees of freedom. Will basically unbias the sample. And we kind of don't go into the math in too much in this class, so you probably have to take my word for it. But if we're calculating on a sample, we need to add this little correction and divide by n-1 rather than n. So for practicality, if you're in a population, you divide by n, and if you're dealing with a sample, you divide by n-1. But what I will try and do is generally I did that for the finance students last year. If people are interested, I'll add a little bit more advanced material to explain a few of these things a little bit beyond the class. So let's just, for the population, let's get my right colored thing back. We have data set 1. We have sigma squared equals 1.5 over 6 equals 0.25. Now sigma, which is basically the standard deviation, which becomes very important, which is just basically the square root of the variance, is going to be the square root of sigma squared. Makes sense. So it's the square root of 0.25 equals 0.5. And for data set 2, sigma squared is equal to 37.5 all over 6 equals 6.25, and sigma is the square root of 6.25 equals 2.5, which comes out beautifully. Wouldn't usually expect that. And if we were assuming that this was just sample data, then for data set 1, we have sigma squared equals 1.5 all over 5 equals 0.3. So again, just divide by 5 over 6. The standard deviation equals the square root of 0.3 is 0.548. They don't have a nice root there. And DS2, sorry, spot my silly mistake. That should be S squared. S squared equals 37.5 all over 5 is 7.5, and the standard deviation is square root of 7.5 equals 2.74. One last little thing. No, I didn't want to take a single calculation out. We've calculated the sum of squared errors. Is going to be sigma, and I'm not going to do the I because I'm too late at the moment, but it's for every observation xi minus x bar squared. So it's basically, we've got every observation subtracted from its mean and squared to get this measure of dispersion. We can actually also write that as sigma xi squared minus sigma xi squared all over n. That's another way of writing this. Now, let me just think, I've already done quite a lot in terms of videos this class. I'll actually upload the proof for that. The proof is relatively simple, or you can look that up yourself. It's just a case of expanding out these brackets. So the first stage of this proof would be to do sigma, then we multiply out, so it'd be xi squared minus 2 xi x bar plus x bar squared. And then what we would do is we'd change all the x bars to sigma x's over n's and just kind of almost go through this sigma x bar squared will be n x bar squared, and you can just kind of go through, and then you'll get this version at the bottom. So just kind of like as a little exercise for yourself, just see if you can prove from this to this. This isn't the homework. See if you can prove from 1 to 2, just to check that you're understanding things reasonably well. Okay, so the last two little things is we're going to do exactly what we did before. So we'll use the population rather than the sample. But it applies to both sample and population. So we want to do what we did before. We want to just understand a little bit more about some of these properties. So what happens if we add C to every item in the data set? Oh, my pen is getting stuck. I don't know if my hands are getting sweaty. So recall, sigma squared, the original sigma squared, so I'll just call this sigma squared 1, is going to be sigma I equals 1 to n xi and we're just going to do it for the standard deviation. So, but it kind of would apply to the variance as well. So sigma I equals xi minus mu squared all over n. And we're going to take the square root of this. And what we want to do is say what happens if we add c to every item. So let's just say add c to every item. Or we'll stick with what the book says. Yeah, we'll still call it. We'll stick with what the book says. This is going to be old. So sigma old. So we're now going to add c to every item. So we'll say we'll call this sigma new is equal to square root sigma I equals 1 to n xi plus c minus we'll call this mu old on the previous one minus mu new squared all over n. But, you know, from what we did in the last video, mu new is, remember, if we add every item, if we add c to every item, then it's basically mu old plus c. So we can actually make this is going to be I equals 1 to n brackets. So that was not a very nice bracket. That's an kind of outer bracket. xi plus c minus mu old plus c outer bracket squared all over n. Okay, and you can see here we've got for every item in the sum we have a positive c, but we also have a negative c, so these guys just cancel out. So we're left with sigma I equals 1 to n xi minus mu old squared all over n which is basically the old kind of, if we go back to where we were, this was our definition of sigma old. So it's basically equal to sigma old. So adding C does not change the standard deviation. And and it's almost, which implies or, I'll say in general, so it does not change sigma or sigma squared. So if we add C to every x, it makes no difference to the standard deviation. And I can show you this kind of, intuitively. Let's just draw a little thing here. And so if we have a mean here, which is x bar 1, and then we maybe add 5, and we have our values, maybe, let's just say we have, our values 1 before and 1 air. If we add 3 to all the other red values, and we add 3 to the mean, we're still clustered around the mean in exactly the same way. Now, it's a little bit different when we go to multiply. So if every score is xi is multiplied by c, then we're going to have sigma nu equals square root sigma c xi, because we're multiplying by c, minus the new means all over n, which is going to be the one thing we can say here, as before, is mu new equals mu old times c. This is again from what we did last chapter. If we multiply every value by c, then, so that box was terrible. If we multiply every by c, then we also multiply the mean by c. So we have sigma cxi minus c mu old squared all over n. And we kind of go on, let's just go on to here. So this is equal to because all this is in a square, we could still have, again, our sum. But everything is in the squared. We can actually take the c out, but because it's squared, it's going to be c squared. xi minus mu L squared, all divided by n. And now we can actually even take it out of the sum, because again, it's just a constant. So it's going to be, so basically we're just moving these c's backwards and backwards and backwards. So it's c squared sigma and again, c squared square root is going to be c, oh, I think I pressed my drawing pen is very sensitive and it's got lots of buttons on it. So it's basically equal to c sigma xi minus mu old squared all over n equals basically, and the one on the right now is just the old sigma. So we'll go back and the sigma nu. So if we multiply every item by c, standard deviation increases by a factor of c. Okay, so that was a little bit more math than we generally get into this class. But again, as I told you at the beginning, I really think that it is important to understand how these means and standard deviations work. You know, what happens if you double your data values? What happens to your standard deviations? Because that's a very good way of, you know, understanding your results. If your results are meaningful, or if your results are fraudulent, or you've made some sort of mistake in calculation. So just having that intuition, you know, my data's increasing, what should be happening to my standard deviation, what should be happening to my variance is quite important. And like one last thing. So let's just square sigma nu. So we have sigma squared nu. That's basically equal to c squared sigma old squared. So if we multiply every by item of c, the standard deviation increases by a factor of c, and the variance by c squared. Okay, so we started off pretty simple. We went through, you know, why we need this idea of, you know, some measure of dispersion, because sometimes the mean is not enough. And we want some idea of the spread of the data with very simple methods. We looked at the range, the interquartile range. Then we looked like taking just deviations and adding them up wasn't going to work. So we looked at this kind of idea of squared deviations, and we called this the sum of squared errors from the data. And then we divided by n or n minus 1 to get our variance, square rooted it to get the standard deviation. And then we proved a few little properties of standard deviation.